La bienvenue à tous les participants et j'ai le plaisir d'ouvrir la session orale avec Monsieur Taibi Ahmed. Donc il va nous présenter un exposé intitulé Ultra-Fast Synthesis of Metal Debris Using Electric Assisted Processing Technique.
Assalamu alaikum. Thanks to the President for the nice introduction. Well, let me first introduce myself. My name is Ahmed Taibi and I'm an assistant professor at the University of Yalma. So for today's presentation, I'm going to talk about the ultra-fast synthesis of metal debris using electric field assisted processing technique. So for today's presentation, first I'm going to start with a small introduction, talking about ultra-high temperature ceramic, also talking about metal debris, including zirconium debris. After that, I'm going to talk about the objective of my research, then move into the experimental procedure, and then we have the results, where I'm going to present my results, including microstructural and also structural properties. And finally, I'm going to finish with a small conclusion. So first, let's talk about ceramic in technology. So in our daily life, we found ceramic in many applications in our daily life. For example, we can find pure ceramic, for example, for teeth and bone replacement. We can find also ceramic in automobile industry, also in aerospace industry. So another application of ceramic is that photovoltaic cell and nuclear reactor. And you can see here many applications of ceramic in technology. One of the family of advanced ceramic is ultra-high temperature ceramic. So this family of ceramics has many properties which make them very important. So one of the properties that they have very high melting point. So the melting points are superior than 3000 degrees C. They are good refractoriness. They have good refractoriness, high temperature resistance, and a good physical properties. The type of ceramic that we are going to talk about today is zirconium debris. So what is zirconium debris? Zirconium debris is one of the most famous refractory ceramics. It is known by the hexagonal crystal structure. Also, they have very high melting point. As I said before, they have a melting point superior than 3000 degrees C. They have also a high hardness, a high electric modulus, excellent ablation and oxidation resistance, also a good thermal conductivity, good thermal shock resistance, and also they have a very high electrical conductivity. The properties of zirconium debris make them used in many applications. For example, we can use zirconium debris in furnace heating elements. We can use them also in high temperature electrodes. Rocket engine also, they are famous for rocket engine, thermal protection structure for space vehicle, and also for cutting tools. So the synthesis of zirconium debris, so we can synthesize zirconium debris by many methods. So we have, for example, solid state reaction method. We have also the electrochemical methods. Also another technique is the chemical vapor deposition, or known by CVD. Also we have sol gel method. And finally, the technique that we are going to study today is the borocarbothermal reduction technique. So the question here, why borocarbothermal reduction? So this is the reaction for the borocarbothermal reduction. So the starting precursor are zirconium oxide, boron carbide, and graphite, or as a source of carbon. So the advantages of this technique is that they produce a high purity and quality ceramic material. Also the scalability, so we can produce ceramic in an industrial scale. Also the cheap raw material. The raw material used in this technique are cheap, so the technique is cheap. So, and also the versatility, so we can use this technique to produce many types of deboride ceramic. However, we have some disadvantages of this technique. One of the disadvantages is the high temperature required. So to synthesize such kind of ceramic, we need a high temperature, superior than 1,500 degrees C. Also the long duration time. So to synthesize this kind of material, we need several hours. It's not a short period of time, so it's for many hours. And also the carbon contamination. As we use a source of carbon, so we find at the end some carbon contamination. So the question here, how can we reduce the high temperature requirement and long reaction time in borocarbothermal reduction? So this is the question. We have disadvantages, how to overcome these disadvantages. So to overcome these disadvantages, we invent a new methodology for synthesizing this kind of material using a borocarbothermal reduction. So we add a technique called flash Joule heating. So this technique, in this technique we use a source of power or an electrical current to produce the material. So the current passed through the sample and the sample self-heated until to a high temperature, and then the reaction happened and we have finally the production of the ceramic material. So this is in brief the technique used in our research. So what are the advantages of this technique? So as you can see here, we have many advantages of this technique. The first advantage is that energy and time saving. By this technique we can reduce the temperature and we can also reduce the time needed for the production of this material. Also the second advantage is that it is versatile. So we can apply this technique also to many other ceramic material. So the third advantage is that no heating source is needed. In the borocarbothermal reduction we need a furnace to heat the sample, but here we don't need a furnace. So just the sample can heat themselves. So, and also the last advantage is the cheap raw material. So these are the advantages of this technique. So the objective of our research is to develop a new universal synthesis approach for the synthesis of zirconium deboride using borocarbothermal reduction assisted by flash Joule heating technique. So we abbreviated by FGIHBCTR. So what is the preparation process of this material? So first we do start with a starting precursor, zirconium oxide, and we have boron carbide, and we have graphite. So we introduce this raw material in a jar for milling, for mixing. So the next step is the mixing. So we provide, we did a rapid mixing for around 15 minutes at a speed of 700 RPM. Then finally we get our mixture. the mixture of raw material. Then we move to shaping. So we have to press the material into a dog bone sample. And after that, we have the flash Joule heating method, which consists of using a source of power to make the sample, to make the reaction happen. And finally, we have our final product. So you can see the difference between the raw material, and finally, we have the final product. So the flash Joule, what do we need in flash Joule heating borocarbothermal reduction? So we need a power supply, which is a source of electrical, a source of current and voltage. We need also we need a MOLI tube where the reaction happens. We need also a camera to record how the reaction happened. And also we need argon, because this reaction happened at under argon atmosphere, so we need argon. And you can see the simplified scheme of the flash Joule heating borocarbothermal reduction. So this is source, the sample, and the reaction will happen. So this is a video which shows how this process happened. So we use a thermal camera to record how the reaction happened. You can see that the temperature we reach, it's around 1400 degrees C, so which is a very high temperature. You can see here, this is the sample in the middle, and the temperature reached was very, very high temperature without the need of a furnace. So we just heat it by self-heating. So you can see here the video. So I record this. This camera is not a normal camera. It's an infrared camera. So where we can record the temperature of the sample. So a rapid heating and then cooling. Now the sample is cooling. And finally the sample cooled down. And we have our final product. So the reaction mechanism. So you can see here how the reaction mechanism happens. So we apply a current to the sample, and then we record. We did the X-ray diffraction for different points of the sample. So at the beginning we see that the X-ray show that only the raw material are presented in the sample. And step by step we see that we move to the formation of zirconium diboride material. Until the end we reach a phase pure diboride material. So you can see here how the evolution of the X-ray until finally we get our final product. And also something important to notice, that the reaction happened only in 1 minute. 1 minute was enough to produce the material. So this is the sample. The next analysis we perform an X-ray and also an ACM analysis of the sample. We can say that the X-ray analysis show a phase pure zirconium diboride. And also for the ACM analysis, we can see here that we have a homogeneous microstructure. Also the EDX results show that the microstructure was homogeneous all around the sample. So, and also the particle size, which is a very important factor. Here we have a small particle size, which is less than a micron. Another important factor in this technique is that we can save energy by using this technique. For example, if we use a conventional method, we have a high energy consumption. Otherwise, by our technique, we can save energy. So 80% of the energy was saved using this technique. So finally, as a conclusion, we can say that the flash Joule heating borocarbothermal technique can have many advantages. One of the important advantages is that we can save energy and also we can save time. Also, the material produced are pure, has a small particle size, and also has a stoichiometric composition. And thank you very much for your attention.
Thank you for the presentation. And
Thank you.
any question, please? Des questions?
I have a question about the chemical structure of zirconium diboride.
Yes.
What's the difference between zirconium diboride sensitive layer and commercial zirconium used by
Well, I show here that I have a, let's see, pure zirconium diboride. So we cannot say that there is a difference between commercial one and the synthesized one. Also, the commercial, they use a synthesis method to produce it. So I think it's the same. And also, I show that the X-ray, in the X-ray, that I have a pure phase zirconium diboride. So I don't have impurities here. So it seems like phase pure.
Thank you.
Any other question?
La préparation de passif.
Oui.
Est-ce qu'il y a une concentration de chaque composé ou la hasard? Le réactif, on va mixer, compresser pour préparer la passif.
pour البريباراسيون هنا في البريباراسيون تاع الباستي واش ديت 1 غرام تاع الميلونج تاعي درتو بريس دونك انا في الاول
الكونسنتراسيون de chaque réactif.
عندي ماشي كونسنتراسيون
C'est la quantité.
انا نخدم بالرياكسيون هذه دونك نقدر نكالكولي لي رياكتيف دونك نكالكولي chaque composition. Après mixer, après ندي 1 غرام chaque pastille. دونك انا شوازيت 1 غرام باسكو درت دي زيسي ولقيت 1 غرام دير لي باستي مليحه. في الكا تاعي كانت كافيه. دونك 1 غرام كانت كافيه.
Donc préparer هذا البرودوي باش نوتيليزي مع قلنا بلي تدي انرجي قليله وهكا الانرجي هذه استعملناها درنا غير 1 غرام.
اسمحي لي هنا كاين كي نهضروا على l'énergie par gramme. J'ai comparé les deux méthodes par 1 gramme. شوفي دونك 35,1 كيلو جول بار جرام. لوطر ثاني كيلو جول بار جرام. دونك سي بور سا باش كانت انا على بالي بلي لا ميثود كونفونسيونيل نحط كونتيتي بزاف ونحط مي انا درت الكومباريزون تاعي بارابور 1 جرام. سي بور سا وي عندك الحق باش تكون كومباريزون يعني منطقيه.
كي تطلع في الكونتيتي اش تعطيك ريزولتا
دونك هنا نرجعوا لابليكاسيون في الاندستري. دونك لابليكاسيون في الاندستري جو سي باسكو مازال لحد الان ما على بالناش باسكو كاين بروبليم في الاندستري كي تكون كونتيتي كبيره راح يصرا دي بروبليم ممكن دي فيسير في ليشونتيون تاعنا ممكن ما نقدروش نبرودويزيو كونتيتي كبيره. دونك هذه جيست غير يسي في لابوراتوار دونك مازال ما ان شاء الله.
Question?
Merci. شكرا.
Passons maintenant à la deuxième présentation.
concernés par la deuxième session poster d'afficher leur poster, s'il vous plaît.